We've established the relationship of altitude to fuel flow in an airplane. Climb higher, burn less. But what about speed? Where does that factor in? Just like in a car, the faster you go, the more fuel you're going to burn. But unlike a car, it's not a linear relationship. Think about drag and the different components of drag on an airplane. The form drag is defined by the equation qSCDo, where Q is the dynamic pressure, S is the reference area of the plane, and CDO is the form drag coefficient. This remains constant for the airplane. Q includes a v squared, that is, the velocity of the airplane squared. In other words, as the airplane increases speed, the form drag increases disproportionately. Induced drag of the airplane is defined by qSCDi, where Q and S are the same, but CDI is defined as CL squared over pi EA. CL, the coefficient of lift, pi, a constant, E, the Oswald efficiency of the airplane, which is usually from 0.6 to 0.8, and A, of course, is the aspect ratio. As the airplane gains speed, lift remains roughly constant, because we're ignoring slight changes in weight of the airplane with fuel flow over the span of just a couple of minutes. As the lift remains constant but the speed increases, the CL has to decrease to compensate. Therefore, the faster you go, the less induced drag you have. If you overlay the induced drag and the form drag on top of each other, you wind up with a curve that comes to a nadir. At the bottom of the curve is the maximum lift-to-drag ratio. Interestingly, the speed for maximum range is not the same as the speed for maximum endurance. The speed for maximum range is found by drawing a line from the origin to a tangent to the drag curve. Mathematically speaking, this is because the maximum endurance is dominated by minimizing CL over CD, which is the bottom of the drag bucket. Maximum range is determined by maximizing the square root of CL over CD. In other words, you're minimizing your lift-to-drag ratio for maximum endurance, you're maximizing your velocity-to-drag ratio for maximum range. Think of it in practical terms. If you're flying, say, a reconnaissance airplane, and you need to stay on a specific target for a long time, you don't really care how far you go. You want to minimize the amount of fuel you burn per unit of time. On the other hand, if you're flying a ferry mission from the United States to Europe to deliver a new airplane, for example, you want to cover the most ground for every unit of fuel that you burn. You're going to think of those two conditions a little bit differently, and you're going to calculate them a little bit differently as well. Now remember, the maximum endurance speed and the maximum range speed are typically fairly slow compared to the maximum cruise speed of the airplane. Performance information is presented for both maximum cruise and for long-range cruise, but those aren't the only two options available to pilots. If you're right on the edge of being able to make a flight, and you need to get there quickly, you can pull back just a little bit and save yourself quite a bit of fuel. If you really need to stretch the legs out, then you can go to long-range cruise and get the most performance out of your airplane.